Okay, good morning. So today we're going to talk more about space complexity, and we're going to talk quite a bit about Savitch's theorem, which is it's a really great theorem. I guess I'll just mention or remind you what it is. Savitch's theorem is the fact that the ST path problem, given a directed graph and two vertices s and t, and the desire to know is there a path from s to t, you can solve this not in logarithmic space, but kind of close, log squared n space. And the idea in Savitch's theorem recurs again and again, actually, in many parts of complexity theory. So we'll see it come up a few more times. And after that, we're going to introduce a new complexity class, non-deterministic log space, which is an interesting class. It's related to Savitch's theorem. So let me actually tell you a little bit about our upcoming plans in the study of space complexity. So one of them, the first thing we'll do after I discuss this is talk about Savitch's theorem and prove that ST path is in this class, all the problems that can be solved in logarithmic squared space. And this is a bit of a funny class. I think actually to draw it, it would look like this. Oh, let me remind you here. This is a diagram of all the classes that most of the classes we've talked about so far. Exponential time. When we only studied time complexity, we had exponential time, NP, co-NP, and P. This picture, by the way, is how most people think the world is. It's possible that some of these classes could actually coincide. So we don't actually know that P is different from NP. So maybe this white space doesn't exist. I guess it's black space, actually. It doesn't exist. But most people believe that all the classes in this picture are distinct. Some of them we know are distinct. For example, we know that P is different from exponential time by the time hierarchy theorem. And then, now that we've talked about space, we fit some more classes in here. For example, logarithmic space and polynomial space. We also know that these two classes are different by the same reason. There's a space hierarchy theorem. It says if I give you more space, then you get to solve more languages. And we saw before that any amount of time that you spend, any time class is contained in the corresponding space class. For example, polynomial time is contained in polynomial space. And conversely, we showed that any space class is contained in a time class that's exponentially bigger. So logarithmic space, for example, is contained in polynomial time. And polynomial space is contained in exponential time. OK, so I was in the middle of saying something. Oh, I was talking about this funny class, log squared space. So this would actually fit into this picture here, as far as we know. It's not an often discussed class, but this would be space log squared. So actually, it contains everything in log space, of course. And in fact, they're definitely different by the space hierarchy theorem. There are some problems that you can solve in log squared n space that you cannot solve in log space, because log squared is like a bigger function than log. And of course, it's contained in polynomial space. That's much bigger. But actually, we don't know its relationship with NP and co-NP. Well, actually, that's not true. On the homework, you'll basically show that NP and space log squared n are different. They're not equal. OK, so let me unwind the stack here. Right, so this is the first thing we'll prove. We'll prove that the ST path problem can be solved in a surprisingly small amount of space, log squared n space. Which is funny. I mean, if you think about the algorithms we know for ST path, like breadth first search and depth first search, they all use a linear amount of space because they mark where you've explored in the graph so far. So they all use at least n space. But you can do it in a very space efficient way. And in fact, once you learn this, you might say, wow, that's crazy. I mean, maybe every problem in polynomial time can be solved in a small amount of space. I don't know, maybe polylog n space. And well, that's probably not true. And so what we want to do in the next couple of lectures is try to identify some problems that might be in this blank space. For example, we're going to want to try to identify some problem, try to find some problem that's in polynomial time, but maybe likely to also need polynomial space. So probably not in any small space class like log space. As I mentioned last time, actually, one problem that's going to be here is the circuit evaluation problem. Given a circuit and an input string, what is the output? And we're also going to try to identify, analogously a problem in here, something that you can solve with polynomial space, but doesn't seem like you can solve it with polynomial time, or even doesn't seem like you can solve it in NP. Okay, and we'll see a problem. The most famous problem like that is a generalization of SAT called, it's basically a SAT where you're also allowed quantifiers like for all and there exists. So that's one task that we want to kind of do. Understand, these would be like a p-space complete problem or a p-complete problem, sort of the hardest problem in these complexity classes. And in order to make sense of that, we'll have to talk a little bit more about definitions and what exactly are reductions in this context and so forth. So that's coming up in the next couple of lectures. OK, and then another thing that's coming up in the next couple of lectures is to study non-determinism, sort of vis-a-vis space. And we'll actually get a little into that today. So of course, when we studied time complexity, we had P and we had exp. But in order to really understand the time complexity of problems that we cared about, like SAT and 3-coloring and so forth, it seemed very useful to invent or to think about this notion of non-determinism, which is like the notion of checkability or verifiability. Okay, and we found that problems like 3-SAT and 3-coloring were complete for NP, which kind of meant that NP is somehow a very natural complexity class. And similarly, we want to understand that, therefore, how non-determinism affects space. And it's kind of interesting. As we'll see, it somehow seems less powerful in the context of space. So for example, depending on time in this lecture, we may or may not prove the following theorem, that NP space is the same as P space. So if I have a polynomial space Turing machine, it can solve some languages. And now if I also give it the power of non-determinism, it actually cannot solve any more languages than it could solve before. Well, it's a bit like a P equals NP in the context of space. OK, any questions before we get started? OK, so great. So let me tell you about Savitch's theorems. Very old theorem, Walter Savitch, 1970, I believe. And, well, there's the statement. The directed ST path problem can be solved with log squared n space. OK, and just remember, as I said, it's very surprising, and it's hard to figure out at first, because breadth first search and depth first search, they all use linear space to mark the nodes where they've been. So how could you do this with super little space? And just to remember, like, a good mental model to have in mind when you're thinking about space, nobody really likes to work with Turing machines. You prefer to just work with like normal pseudocode. And in normal pseudocode, you would usually have variables. You can think of that like as like an int data type in C or something. Something that stores a number between 1 and n, or 1 and polynomial and n. So for example, like a variable can store the name of one vertex in the graph. OK, that's fine. And you can imagine that you can look up whether or not you write down the names of two variables. You can like look up whether or not that's an edge in the graph or not in constant time and no additional space. So these variables that hold numbers between 1 and poly n, on a Turing machine, you can write that down with log n bits. So somehow like one variable in pseudocode is kind of like log n bits on a Turing machine, typically. OK, so a problem that can be solved in log space is one that can be solved with like a constant number of variables. OK, and we're going to show the ST path is in log squared n space. So it's going to be sort of solvable in pseudocode with about log n many variables. So the algorithm might allocate an array of about log n size and then solve the ST path problem. OK, so how are you going to do that? Well, the idea, it's a nice idea. We said, breadth first search does not work. Depth first search does not work. The idea, it's a great idea. This is really the key idea of Savitch's theorem is, you might call it middle first search. What do I mean by that? Let me just try to, say in words what I mean. Like, OK, you're given a graph. It's got n nodes. You're trying to decide if there's a path from this S to this T. OK, if there's a path, it's going to have length at most n, right? Because, there's no reason to visit a vertex twice. So what you're going to try to do is guess the middle node on that path. This is the high-level idea. Or guess a middle node on that path. And by guess, I really mean like just try all possibilities for what the middle node could be. OK, and so as you cycle through all the possibilities, you really only need like one variable for that. Like for v equals 1 to n, you could try to see if v could be a potential middle node. And then what you kind of have to do, you kind of have to ask recursively, is there a path from S to v in at most n over 2 steps? And is there a path from v to t in at most n over 2 steps? OK? And the depth of this recursion, every time you kind of do a recursive call, you're going to ask about paths of length n over 2, and then n over 4, and then n over 8. So the depth of the recursion is going to be log n. Okay, and that's the basic idea. You'll have a log n depth recursion. And kind of at each level or at each recursive call, you'll be using a constant number of variables. Because basically within that recursive call, you'll be cycling through all possible potential middle variables on the path. OK, so that's the idea. And I'll write some more about it now. So I'll try to write it in pseudocode. So we're given a graph, a digraph, G on n nodes. OK, and remember, eventually we should think about how to do this on a Turing machine with a read-only input tape that describes G and some work tapes that are supposed to just use log n bits. But for example, last time I talked about how you can compute n, so log n space to compute n. And also, remember here, n is not the length of the input. For graph problems, n is usually the number of vertices, but that's also fine, right? The Turing machine can initially go over the description of the graph and compute n and write it down. OK. And it's also given, S and T in the vertex set. And basically, here's the algorithm. As I said, it's recursive. So we're going to, let's say, have a recursive function I'll call path question mark. And it'll take 3 inputs, x, y, and k. These are nodes. This is a number. And the idea of it is that it's supposed to return true or false. Is there a path from x to y of length at most 2 to the k? You might have expected me to say length at most k. Somehow it'd just be like a little bit more convenient to ask, let k be the logarithm of the length. So whether there's a path from x to y of length at most 2 to the k. OK, so we're going to try to implement, well, in pseudocode, this function. OK, and assuming we can do this, what does the actual algorithm, overall algorithm, do? Well, of course, overall algorithm will just call path st, and k will be the ceiling of log n. OK, because, as I said, if there's a path from s to t, then there's a path of length at most n. OK, so 2 to the ceiling of log n is maybe a little bit bigger than n, but that's fine. So this is sufficient to check. And of course, even a Turing machine can compute this ceiling of log base 2 of n. It's actually just basically the number of bits when you write down n. You can add 1 to that or something if you want. OK, so is the overall plan for the pseudocode clear? I mean, we're going to just talk about how to get a low space implementation of this function. All right, well, I think you can easily write it, or you can help me write it here. What will the pseudocode for this be? Well, let's start with the base case. So if k equals, what's a good base case? What's the most popular? Yes? Yeah, 0, good. Then k is 0. What problem are we trying to solve? Is there a path from x to y of length at most 1? So what should we do? If and only if what? Yeah?
X, Y is in the intercept.
That's what I had in my notes, too. Then I realized it was incomplete like 10 minutes later. Or, right, I forgot about that. Or x equals y. That's right. OK, else return false. And that's because the definition is whether there's a path of length at most 2 to the k, so at most 1. So if there's a path between x and y at length 0 if x equals y. And it's actually important because otherwise, it'll only find paths of length exactly 2 to the k, which might not exist. OK. Otherwise, all right, that's the base case. Well, we just implement this thing that I said. So for each node v in, I'll write w in v, just like a little for loop. Well, you could say, let me just write this. Return, so recursively call a path from S, W, and k minus 1, and path W, T, k minus 1. All right. That's the whole algorithm in pseudocode for the ST path problem. So let's first think about the correctness. What do we think about the correctness? It's correct. Yes?
Don't you only want to return if that's true, and otherwise you want to keep looping? You don't want to return in all cases.
Oh, yeah. Good point. Okay. Not correct. Is it not correct? Yeah, let's see. We want to, right. We want to OK, good. So we should instead say this. Thank you. So what should it say?
If return true.
Yeah, that's good. Otherwise, yeah, kind of go on. And then, here, return false. Is that better?
I think, don't we also want to use x and y?
X and y. Thank you. And put 2 x's here. We're very wrong. Okay, there's probably a third mistake up here. How's it looking now? Yeah?
It doesn't matter that you include x as y and y as well as w. W could x and yes.
I think you want to do that, actually, because, well, actually, it probably doesn't matter. It probably doesn't matter.
You need that.
Do you need that? I mean, it doesn't hurt. I guess you need that. Well, yeah, like, for example, suppose the graph had no edges, but you called it with x equal to y. So for any value of k, even a value of k bigger than 0, the correct answer would be yes. There is a path from x to itself of length 0. But if you tried to find that path by going through any other vertex other than x and y, you would fail. So I guess you do need to like allow the w to be x or y. That's trickier than I thought. Good for you, Walter Savitch. OK, so how do we feel about it now? Now is it better? It's OK? I should probably prove this, but I'm going to not prove it. OK, good. All right, how about the space complexity? That's what we really care about. Well, OK, really, we should have put this onto a Turing machine and imagine the space complexity there. But let's just talk for a while about, like maybe we'll just, nobody wants to get into Turing machines too carefully at this hour. So let's talk a bit about the space complexity, starting with the pseudocode. So let's see. I mean, we're talking about this overall algorithm. I mean, what does it need to store? It stores n, like globally. OK, and then like in the recursion, it's storing like x. Maybe it also stores s and t globally, and x and y. And it like cycles through w. Of course, an important point here is like it doesn't like first write down all the w's and then try each one. Like it reuses them. I mean, it doesn't have a different variable for each w. So it uses w. I don't know, like maybe you use like a variable storing true or false for the return values of these things, but that's like 1 bit. K, I guess. K is actually super small. Like actually to store k, you only need log n bits. But whatever, I mean, you could store it in like 1 variable. So that's good. So basically, I mean, if you look at the pseudocode, right, there's constantly many variables. So it's just like log n bits on a Turing machine. So did we show the problem is in L? Saw a shaking head. No, why not? Yeah?
While we're doing the recursion, we still need like I guess the column variables for the previous call of the recursion, so we can't just like overwrite those.
That's right. Like, you know, recursion ain't free. Like, it looks nice and free, but you know, at the end of the day, I mean, whether it's a Turing machine or it's your like x86 assembly language or whatever, I mean, recursion doesn't happen just by magic. Like, you need to implement the recursion. So the recursion is not free. You need to implement it. And how do you know, actually implement recursion? With a stack. Right? Hope you've learned this in your life. So, so you need to implement it using a stack. You know, called stack. So, you know, when you actually do a recursive call, you kind of like save all your current state, which is like a, you know, some kind of stack record that has the values. I mean, you could probably be a little bit more efficient than this, but basically, you know, you have to save your state in some kind of like stack record that stores, you know, all the local variable values. And maybe also like sort of the position in the code. I mean, basically, you have to, when you do a recursive call, you have to kind of write something down to remember like if you were here or if you were here. Okay, and then when you're about to do that recursive call, you have to like push all this stuff onto the stack in a record. So each record on the stack uses order log n bits to store all these local variables, 3 or 4 or 5 local variables. And what's the depth of the recursion? What's the maximum number of records you ever get on the stack? Well, we talked about this. It's pretty easy to see that it's, literally maybe log n. Okay, because every time, you do a recursive call, k goes down by 1, and it starts out at log n. Okay, so I'm not going to try to, it's actually not too terrible to like write this out like exactly how you do it on a Turing machine. You would have one work tape whose job would be to contain all these like stack records like separated by punctuation, and some other like work tape to access the stack and do the calling, do the actual code in a recursive call. But I hope you can imagine it. Okay, so this is how on a Turing machine you can do this in log squared n bits space. Okay, because at the worst, you're like halfway through the recursion or most of the way through the recursion. You have like log n things, like kind of call records, and each one is saving log n bits. Okay, so actually I want to say that's it for the correctness and the space complexity, and actually for the theorem, really. Any questions? Okay, great. So cool. That's how you can solve the path problem in a very small amount of space, log squared n space. And you see, it's like, space complexity is a little bit fun because, you sort of think about algorithms in a new way. How you're not trying to maximize the thing you normally, or minimize the thing you're normally trying to minimize, time. You don't care about time. You're just trying to use as little space as possible. And it introduces some new algorithms. In fact, I kind of mentioned this last time. Here's an exercise for you to figure out the time complexity of this algorithm. Well, it's pretty easy, right? Actually, there's like a recursion, T of n is basically like n plus, because you do about order n work inside each loop, 2 times t n over 2. Because you make 2 recursive calls, and like k goes down by 1, which really means like n is going down by 2. I think I got that right. Anyway, it's an exercise. Maybe it's wrong, but you will find that the running time is n to the order log n. So as I mentioned last time, this is not even a polynomial time algorithm. Hey, that's OK. We're just trying to get to log squared n space. You might ask, is there an algorithm that uses both polynomial time and log squared n space? That's unknown. That's an interesting question. Cool. Let me ask you one more question. I won't write anything, but I didn't, either in the pseudocode or in our imaginings of what it would look like on a Turing machine, I didn't get into the question of like, oh, how is the graph stored? Is it like a adjacency list? Is it adjacency matrix, or what? Does it make a difference? Yeah.
No, because we can easily convert between forms before we do it.
I like the first part of your answer, no. But the second part, I'm not so sure about, because it's true, normally you don't mind because you can convert between the 2 formats. But this could cost you a lot of space. So let's say, remember in the space model, the input is written on a read-only input tape, which doesn't cost you space. So let's say if it's storing in an adjacency, I don't know, list. And now you want to say, oh, I wish I had an adjacency matrix. Well, if you want to write down the adjacency matrix, you can, but you have to do it on your work tapes. And then the size of that is like n squared to write down the adjacency matrix. So unfortunately, yeah, you cannot just write down the new input format. Yeah?
It doesn't really matter because time is free. It's like
Yeah, it doesn't matter because let's look a little bit, and this will be important later actually. How does this algorithm actually, when does it actually read the input? Well, I guess a little bit at the beginning when it figures out what n is, but there it doesn't really matter. I mean, OK, it has to know what n is. But actually, this algorithm only reads the input right here. And so you see, what is it doing when it's reading the input? It's got some node name x written down and some node name y written down. And all it wants to know is this an edge in the graph or not? So somehow the only way it needs to access the input is by sort of a lookup for edges. It has x and y written down. Now it wants to know yes or no, is that an edge? And then if you have a read-only input, we often care about adjacency list versus adjacency matrix in terms of like, time efficiency for doing this, like figuring out if an edge is in there or what. In space, we don't care. We just need, is it possible to find out whether or not the edge is in there without, let's say, using extra space? And that's possible in either format. I mean, you just basically search through the input to see if x, y is in there. So this is the thing to remember. Like, it doesn't exactly matter how the input is stored here as long as you can efficiently, in terms of like not using more space than log n, figure out if a given edge is present or not. Great. OK, so that's Savitch's theorem. We proved it. And it's going to be quite useful. I mean, it's another nice example of like how complexity theory is in many ways all about algorithms. I mean, that was an algorithmic result. And we're going to use it like several times to study complexity classes. So OK, so now is the time. We're going to begin a little bit of part 2, studying non-determinism in the context of space. OK, so in particular, we're going to talk about a new complexity class called NL. OK, so this is the non-deterministic version of L, of log space. So it bears the same kind of relationship to L as NP does to P. OK, so every time you introduce a new complexity class, you have to ask, like, what are you doing with your life? Like, why put like another complexity class into the picture? And the thing that I really believe is, the complexity class is important and it's worth studying and you should care about it or introduce it. Like, if and only if there's a problem that exactly captures that complexity class. Basically, if there's a nice problem, a problem you care about, which is complete for that class. And it's going to turn out that the ST path problem is complete for this NL. So this NL class, non-deterministic log space, is like exactly capturing the complexity of whether, the problem of whether or not there's a path from S to T in a graph. And that's it's a super natural problem. So therefore, NL is a worthy class to study. But we're going to define it in terms of, non-determinism in the context of log space. So actually, when we first introduced NP, we did it with like a verification definition, the verifier and the certificates and so forth. And then later we were like, well, there's a totally different definition using this concept of non-determinism. We invented this non-deterministic Turing machine and said NP was polynomial time for non-deterministic machines. And then we decided that these were actually the same class, NP. So OK, when it comes around to defining NL, we could try to invent a verification definition. Or we could take the non-deterministic definition and see what happens. Well, it turns out what we're going to actually do is take the non-deterministic definition. Let me say a few things about how you might try to make a verification-based definition. The first thing you might say is, well, I want to talk about proving things or verifying things, but in logarithmic space rather than polynomial time. So you might try like a definition where like, OK, there's a read-only input x, and then you get some kind of certificate y. Then you have to ask yourself, well, should y be polynomial length in x, or maybe logarithmic length in x? Well, the right idea turns out to be that like y should have length polynomial in the length of x. And y should also be read-only. And then, it's sort of the same definition as NP, but maybe the verifier only uses order log n space. I'm not writing out a proper definition here because we're eventually not going to focus on this definition too much. But you might say, hey, let's say maybe this is NL. Same thing as like NP, but the verifier can only use log space instead of polynomial time. And then maybe it's read-only inputs and certificates because that's how we measure space. Actually, if you make this definition, turns out you get NP. Surprisingly, that is not very easy to show, but it will kind of eventually be able to show it. So somehow, if you do this, it's sort of the wrong definition of NL. Now, you can convert it into like the right definition of NL, but you have to upgrade y being read only to y being reads once. So like it's not just like you can only read y. You can actually only like make one pass through y from left to right. And if you make that definition, it corresponds to somehow the right definition of NL that we'll get from non-determinism. And I think you'll explore this on the homework, which I haven't quite finished writing, but I think it'll be on there. But that's all I want to say. So it's actually not extremely clear how to make the best definition of NL using verification. In some ways, actually, whenever we add non-determinism to a class, it's sort of better to use non-deterministic Turing machines. But somehow for NP, we kind of tell you the verification definition first because it's more natural. But we're tough people. We're now going to just use non-deterministic Turing machines. So OK. So here we're going to officially define NL. Now, we may as well just define non-deterministic space, just like we define non-deterministic time. So more generally, non-deterministic space, f of n, is a complexity class. It's just like the space complexity class we already defined, except with non-deterministic TMs. So it's all the languages A, such that there exists a non-deterministic TM M using order f of n space on each branch or like process. I'll remind you a little bit about this in a second. On its work tapes. Yeah, I should, of course, add it decides A. OK, so remember non-deterministic Turing machines. Actually, we first talked about non-deterministic pseudocode with like these go-to boths. And it's sort of like you imagine that the computation sort of spawns a whole bunch of branches. And you have to use at most this much space on every branch, but not in sum. Just each branch uses at most this much space. And then remember the definition of like a non-deterministic computation accepting a string. It accepts if at least one of the branches accepts. Like if there's some way to trace through the code, making these non-deterministic choices such that the string is accepted. Yeah? No? OK. OK, or you should also, really, you should really imagine the homework. We talked about like the real Turing machine-based definition of non-determinism with like the Sipser TMs and everything, where basically you have two transition functions instead of one transition function. You have a transition function delta 0 and a transition function delta 1. You kind of imagine that the Turing machine can do either one, delta 0 or delta 1, at each step. And like it accepts if there is a way for it to use some delta 0s and delta 1s along the way to get to an accepting state. Still look like you want to ask a question.
You said that L and NL were the same, right?
No.
Which two were the same?
It's going to turn out that NP space is the same as P space. Yeah. But we'll get there soon. So, OK, so let me just use this since I have it here. OK, so we can define like NP space. That's just n space where you can put any polynomial function here. And you can do that. We're going to first focus on NL, which is n space log n. Okay, so it really might look like we're getting into obscurities here, like the weeds, like we're like saying, OK, let's take all the languages that can be solved by non-deterministic Turing machines using order log n space. Like it's getting a little wacky. But as I said, this class is going to exactly capture the computational complexity of the path problem. And that's such an important and natural problem that it's logical to introduce this class. OK. And great. So we have this class NL. Where does it fit in the picture? Well, it contains L because a non-deterministic Turing machine can use no goto boths, or its delta 0 can be the same as its delta 1. It could just be deterministic if it wants. So you can certainly do any language in L, in NL. We'd be more interested in upper bounds on NL. So we're going to prove actually two theorems sort of simultaneously. And that's NL is contained in P, and it's also contained in deterministic space log squared n. And we may or may not complete the proofs of these theorems today. We'll get started on them. Maybe we'll finish them. Maybe we'll finish them next time. But as you'll see, NL is really tied up with the complexity of this path problem. And we know that the path problem is in P by like breadth first search or whatever. And Savitch's theorem tells us it's in log squared n space. So this is going to be like the reason that NL is in these two classes. OK, so I guess, can I draw it here? Yeah, somehow. I didn't give myself a good amount of space. This was L, and then somehow NL is like contains L. It's contained in P. It's contained in log squared n space. OK, so like L is contained in NL, is contained in P, is contained in, et cetera. OK. So before we get there, I mean, it's a little bit not nice to just invent a class and then start proving theorems about it. I mean, let's like see NL in action a little bit. Like, let's see a problem in NL. And, well, it's going to be the path problem. So here is a proposition we'll prove first. This ST path problem is in NL. OK, so if I want to know if there's a path from S to T in a directed graph, I can do that in logarithmic space if I have non-determinism. So Savitch's theorem said we could do it in log squared n space with normal computation. We'll do it in log n space with non-determinism. OK, so I'm going to give the pseudocode for this. But I'll talk a little bit about Turing machines. So here's the pseudocode. And basically, the idea is like guess a path of length at most n. This is the idea. So the non-deterministic machine is kind of going to start guessing a path. And if it finds a path, it'll accept. And if it doesn't find a path after sort of n vertexes of guessing, it'll reject. And so it'll have the right behavior in terms of what it means for a non-deterministic algorithm to accept, right? Like you accept if there is some way for the guesses to turn out or the goToBoths to turn out such that you accept. So like if some path exists, and if all the branches or all the guesses don't pan out, then the overall thing rejects, which is what we want. And the main thing to sort of check is that you can do this while reusing all of space. So it's not like you just, at the beginning, guess the whole path and write it all down and then check that that path is in there, because you don't have the space to guess the whole path, right? To guess the whole path would take you like n times log n space. So you kind of just guess the path in like an online fashion. So actually, I'm going to need a bit more room than this. Let me go up here. OK, so now I'm going to write pseudocode for a non-deterministic log-spaced algorithm for checking if there's a path from S to T. OK, so on input G and S and T, let me just say the first line of code is if S equals T, then accept. OK, that's just the base case I want to get out of the way. And OK, let me just put some other like base case stuff here. Like now, deterministically compute n. OK, we kind of always do this in log space algorithms. Just let's warm up by figuring out what n is. That's log n space, which is the size of V. OK, and now let's get going. I'll write the main code. So here it is. Say cur node colon equals S. Then for I equals 1 to n. I'm going to imagine that the vertices are named 1, 2, up to n, just for simplicity. OK, and this also like uses log n space because it's one variable that stores a number between 1 and n, log n bits. OK, and we're just going to now use non-determinism to like guess the next vertex in the path. This is just like, this I is just keeping track of the time, like how many guesses I make. Maybe I should call it L or something for length. I'll call it L, why not? OK, so using goToBoths, if you want, will, or like really on Turing machines, using the fact that like you have 2 transitions that you can use. So you have one transition that writes a 0 and one transition that writes a 1. You like write, or this is normally called guess, a node, it's a U in V. Okay? This is basically, honestly, how non-determinism always works. I mean, you technically have all these goToBoths or whatever, but basically you use it to just like write down an arbitrary string. So like this thing, you can imagine it like forks off like n different branches by just non-deterministically writing down a string of length log n, or more precisely, a node U. OK, so each branch just writes down a different U. OK, and that's log n space. OK. And then, it's trying to, amazingly and miraculously guess like a perfect path from S to T if it exists. And it's just guessed that like the next node I should go to is U. Whoa. How did that happen? I guess somebody really wants to make this not happen. It's Pretty cool. All right. Watch it do it again in a second. That'd be awesome. All right. So, all right. So now we're going to guess that this is like a valid next thing to do, or check that this is a valid next thing to do. So we're going to just say, hey, let's now check if cur node u is actually an edge in the graph. OK, that's just like one lookup into the input. You know, again, this only accesses the input by just checking if a particular pair is an edge. And if so, then we'll do, we'll just do cur node equals u. And sort of go on. And then we'll also actually check, like, did we get there? So like if, let me write cur node, which is now u, equals t, except. It's like, hooray, we got there. Else, this else is with respect to this cur node u being not an edge. And you might say, oh, if it's not an edge, well, maybe we'll try another vertex. No, just reject. Just like, well, you made a bad guess, friend. So let's reject. OK, and then if you finally get all the way to the end of this loop without having accepted yet, or having rejected, then it's kind of like you've guessed the algorithm's like, or the branch is like guessed a sequence of like n nodes, and they've all been legal edges. It just never got to t. So we'll just reject here as well. OK, so that's the pseudocode. Any questions about it? So let's talk about it. I mean, again, you should really do this on Turing machines, but I'm going to leave it at the pseudocode. First, let's see the space. And remember, you're just analyzing the space on like one particular branch. So you just want to say, like, no, how do the goto boths turn out, or like whichever u it writes down when it uses its non-determinism. We just want to make sure it doesn't use more than log n space. And it doesn't, right? Like, I mean, it basically uses like 3 variables, maybe like cur node and L and U. That's it, each of which is log n space. So yeah, so it's like order 1 variables on all branches, which is like order log n space. I'm just going to put a check. And now we want to also just check correctness. So we should really check 2 things. That if there really is a path from S to T, then this non-deterministic algorithm accepts, overall accepts. And remember, that means there's at least one branch where it accepts. And if there is no path, then it doesn't accept. So no branch accepts. Let's check that. Say, if some S to T path exists, then at least one branch accepts. And this branch is really like, a set of sequence of guesses. Accepts. Let me just say that's true, right? I mean, say there is some S to T path. It's of some length that is not necessarily n, but at most n. Maybe it's like S, then U1, then U2, then U3, then U4, which is T. OK, so when you're going through this loop, as long as this thing perfectly guesses the correct next vertex, then every time this edge really exists, and when it gets to T, it accepts. So it might accept, at some point, some value of L that's less than n. So that's that. And conversely, if at least one branch accepts, Well, we need that this implies that there exists an S to T path. And let's look at the code, right? The only possible way a branch can accept is if it managed to correctly guess a sequence of nodes U such that it was always an edge and it ended in T starting from S. So it's correct. Any question? Yeah.
How are the space classes closed under, like right now we're considering just like decision problems. Like how are the space classes closed when you're trying to consider like search problems or something like that?
So great question. Right. So far we've only talked about decision problems. And we're going to get into that. So we haven't really talked about what it means to solve a search problem or a function problem in log space. And sometimes it's clear that you can say a search problem is solved in log space. If the algorithm can even just like write down the answer like it normally does for search problems on a tape in log space. But actually, eventually, we're going to want to start talking about solving like a search problem where maybe the input length is n and maybe the output length is also n. Still, we're going to want to talk about solving it in logarithmic space. So it doesn't have enough space to sort of write the output. But just like we kind of don't want to charge the algorithm for the input, we sort of don't want to charge it for the output either. So you could say that, oh, it has a write-only output tape. But eventually, we're actually going to do something even a little bit more subtle than that. So hold on to that question. So it's going to be interesting, sort of a little bit, what it means for a logarithmic space algorithm to solve a non-decision problem, a problem with output. But actually, thinking of it having a write-only output tape is pretty reasonable. OK, so good. So now I proved this. ST path is in NL. And now we're going to get started on proving these theorems. We might finish, or we might wrap them up next time. OK, so this is the sort of much harder theorem. We have to say that any problem that can be solved by a non-deterministic log space machine can also be solved by a polynomial time machine. And it can also be solved by a deterministic log squared n space machine. So in order to do that, we really need to get into the nitty-gritty of non-deterministic log space Turing machines. And the configurations, in particular, that we talked about last time. So let's remember a picture of such a machine. So it's got this read-only input tape. And again, this is kind of a simulation result, right? We want to show that if a non-deterministic log space machine can do something, we can construct a polynomial time algorithm that does the same thing, and so forth. So I'm going to say, look, OK, give me a non-deterministic log space machine. I'll simulate it. So it'll help our lives to make it simple. So we're going to assume that it only uses one work tape, which we can do without loss of generality, we know. OK, so it's got a read-only input tape. It's got a work tape. It's got, here's the machine. It's got some head that points to the input tape, some head that points to the work tape. And it's actually non-deterministic. Maybe I should call it n. And so that really means it has two transition functions, delta 0, delta 1. And the branching comes by every step, you imagine what would happen if it used delta 0 for transitioning. And every step, what would happen if it used delta 1 for transitioning. And so that sort of you get all these, you don't get a deterministic computation path. You get this binary tree kind of computation paths. And as we know, at the end, each one either accepts or rejects. And the machine overall accepts if at least one path gets to an accept state. OK, this is not the idea of this proof, so let me get rid of it. So I want to talk about configurations again, like we did last time. Remember last time we proved that log space is in polynomial time. We proved L is a subset of P. We really showed that space F is in time exponential in F. And we did that by saying, well, if you have a space F machine, you can consider all its configurations. There's basically at most exponential in F of them. And you cannot go through any configuration more than once. Otherwise, you'd have an infinite loop. So you can use at most exponential in F time. And we took F to be log n, and we got that L is contained in P. Now we're going to show like a bit of a harder result, that even NL is contained in P. It's stronger because NL contains L, but we're going to show that even NL is in P. So we're also going to need to talk about the configurations. So remember, configuration of n on x. It's not quite the definition of configuration we use when studying time, because we use a bit of a different notion when there's a read-only input tape. So basically, it's something that looks like a string C, which contains, like the work tape. And then, it's got a state in here, Q, 7 maybe, and PE. So this encodes what's on the work tape, what state the machine n is in, where the head is pointing. The head is pointing to wherever's to the right of the state symbol. And then we said, oh, we're also going to tack on, the pointer, the position of on the read-only input tape. Okay, so we said this is our definition of a configuration. It kind of is like a snapshot of what state, the global state, the Turing machine is in at a given time on an input x. And it includes everything you need to know in order to understand what will happen in the next step. Okay? Everything you need to know about what will happen in the next step of the computation, even the non-deterministic computation of n, depends on the work tape, what state it's in, what symbol it's reading on the work tape, and also what symbol of x it's reading on the input tape. And that's determined by this input tape position here. So x is always considered fixed. And this is a semicolon. Okay, and this in general is like a number between 1 to n, where n is the length of x. And so one thing we checked, in general, if the work tape has space f of n, then we check that there's at most 2 to the order f of n different configurations. Here we're just fixing log space. So here it's a log space machine. So there's at most 2 to the order log n, which is polynomial in n, different configurations that this log space machine can be in. And if this were deterministic, in the deterministic case, there'd basically be this next configuration function, which depends on a deterministic machine m and x, which takes sort of one configuration and it just spits out what is the next configuration that the Turing machine would be in. It would look very similar. The state would change, and maybe the head position would move, and maybe maybe the symbol would change, and maybe this would go up or down by 1 or stay 12. But that's how a deterministic machine computes, right? You just go through all these configurations deterministically. And in the non-deterministic case, I know we never exactly formally defined non-deterministic Turing machines, but except on the homework, so I have to use that definition. In the non-deterministic case that we're actually studying, well, it's just like there's 2 next configuration functions. Each step uses or branches uses delta 0 or delta 1, or in pseudocode it could be each step is a go to both. You can kind of imagine in pseudocode that every line has a go to both in it. You can, if you don't want that, you can just have both the go tos be to the next line. And therefore, it's like there's a next config 0 function and a next config 1 function. Okay, and these things depend on the definition of n and also x. Okay, so for a non-deterministic Turing machine on an input x, given any configuration, there's 2 different configurations that you could go to or branch to. So the picture of what's going on is like this. When you picture the computation of a deterministic Turing machine, it's kind of like a path graph. It just starts in the first configuration, and then it goes to the next configuration, and then it goes to the next configuration, and it goes to the next configuration until you get to a configuration that has either an accept state in it or the reject state in it. And in a non-deterministic non-deterministic computation, there's branching. And as you saw in the homework, it's like without loss of generality, it's like 2-way branching at each step. So the computation of like a given log space, I should have said this here. This is a log space non-deterministic machine. So given n and given the machine, the computation trace kind of looks like this. There's a starting configuration, which maybe I'll call C start. Okay, and what is this? It's just the initial state, and then maybe you have a blank here to say that there's nothing on the work tape, and the head of the work tape is pointing to the first character, and then the head on the read-only tape is pointing to the first character. So let's, this is the starting configuration. Okay, so this is like the computation trace, if you will, or configuration diagram of n on x. Okay, and then it has 2 transitions based on, next config 0 and next config 1. And this will take you to some other configuration, C, some C prime. These will, maybe this could be like, I don't know, A, Q, 3, blank, 2, something like that. And then it has 2 possible transitions, and this has 2 possible transitions. And what you can imagine is that, one thing you can do is just write this all out as a big binary tree. And then at the leaves, well, you'll get a leaf when you get to a halting configuration, one with either an accept state or a reject state. And then you would say the overall computation accepts if there's at least one leaf that's accepting. But now I want to do something a little bit different. I want to draw a little bit of a different diagram. All I'm going to do is I'm not going to draw it like a binary tree. I'm just going to write down all the possible configurations and make a graph. So in other words, it could be the case that the configuration, if you do transition 1 out of this state, it could be the case that it actually takes you back to exactly this configuration. So instead of just writing C prime down here again, I'm just going to only write every possible configuration once, and I'll just put in all the arrows. Okay, so what I'm saying here is this the non-deterministic computation of n on x induces a directed graph called the configuration graph, which I'll write as, I don't know, maybe script G, where the vertices of G, I'll even call it VE. V is the set of all configurations so in particular, V is of size polynomial in n, well, at least when n is log space. Right? Because as I reminded you, for log space machines, the total number of possible configurations is polynomial in n. N is the length of x. In general, the size of V would be 2 exponential in the space usage of n. And C prime is an edge. If and only if C prime is like the next config, either 0 or 1 of C. Okay, so actually in this digraph, this configuration graph, every non-halting configuration or vertex has out degree 2. Okay, so we put down a vertex for every possible configuration. There's polynomially many of those. And for every one that's not a halting configuration, that doesn't have the accept or the reject state in it, it has like 2 outcoming arrows. One for like, it's like a go to both, like one for using transition delta 0 and one for using transition delta 1. It's allowed that both arrows go to the same vertex. So it might effectively have out degree 1 if both of its out edges go to the same configuration. That's fine. It sounded like I was in the middle of the sentence, but I'll just stop that sentence. Yeah. And let me just add that. So given n, the log space non-deterministic machine, and x, the length n input, we can at least imagine drawing this graph. Okay? I'm not saying any algorithms or anything yet. Just given n and given x, one can imagine this graph, the configuration graph. It has poly n many vertices. It's a directed graph. Every non-halting vertex has out degree 2. And, by the definition of non-determinism, or non-deterministic acceptance, determinism, n of x accepts if and only if there's a path from C start to an accepting configuration. Right, literally any configuration, each vertex is a configuration, any configuration where the state symbol is Q accept. Any question about that? So this is kind of cool, right? Because it's sort of, okay, it's getting back a little bit to the path problem. It says if you're trying to understand whether this non-deterministic machine n accepts or rejects on a string x, it boils down to whether there's like a path from like a designated start vertex, well, to an accepting vertex. So each of the vertices with no out edges is sort of labeled either accept or reject. We kind of want to know, can you get to an accept vertex? So it's quite similar to stpath. In fact, we can make it essentially identical to stpath with another little trick. It's mildly annoying that the definition of acceptance is whether you can get from C start to some accepting configuration. It'd be a little bit cooler if you could say, oh, it accepts if it gets from a special start configuration to a special finish configuration. And you can't quite do that because, the Turing machine, a Turing machine can accept in many different states. Like it can accept with some random junk written on its tape. This head could be here, it could be here, it could be doing anything when it decides to finally accept. But actually, we can make it without loss of generality that it always kind of gets to the same configuration when it accepts. So what do I mean by that is, if n is a non-deterministic log space machine, without loss of generality, and this means without changing the language it decides, without changing which strings it accepts or rejects, and without changing the fact that it's log space, we can assume it cleans up after itself before it accepts. Okay, it's just good hygiene. Can assume that right before it ever accepts, some slanty writing, ever accepts, it erases its work tape. This means writes blanks. So it just writes blanks over top of everything that was on its work tape. Moves the work tape head to the start. For this, you need a little trick for Turing machines. You should just modify the machine so that the very first thing it does is puts a mark where the start was. Actually, it probably doesn't even really need to do this depending on how you define configuration. But anyway, just so it knows where the start is, it can clean everything up and move its head back to the beginning. And also moves the read-only tape head to the start, okay, and then accepts. Okay, as I said, this is without loss of generality. It doesn't cause the Turing machine to use any extra space, just cleans up the space it already used. And it doesn't change whether or not it accepts a string or not. It just delays a little bit, but we don't care about time for this. Yep?
There legitimately is a non-halting configuration that just happens to be, read. Is at that place the tape is empty will that cause an issue?
Oh, if it already had the property that sometimes it accepts when it's in this cleaned up state?
Or it has somewhere during its process that it actually hits a state like this, but it's not actually about to accept it.
That's OK. So let me say one more thing, and then maybe it'll be a bit more clear. We're going to only sort of define this cleaned up state to be the special state if it's also in the, if the Turing machine is, I should say, cleaned up configuration to be the sort of final configuration if it's also in the accept state. So all I'm sort of saying here is, once we do this without loss of generality, we can say now, whenever, if ever, n of x accepts, it's always exactly in the configuration, well, this one, q accept, and then blank, and then 1. So it looks almost exactly like the start configuration, except it's got q accept there. And we'll call this, C sub accept. Okay, so this is a good point to basically stop. So without loss of generality, we can actually assume this. And so then we can change this statement to n of x accepts if and only if there's a path from C start to C accepts. And this is going to be really great for us in terms of understanding NL. It basically says whether or not a non-deterministic log space machine accepts or not is exactly the same question as whether there's a path from a certain node to another certain node in a poly-n-sized directed graph. Slightly tricky bit is this graph is sort of implicitly given by the nature of n and the string x. OK, but we're almost there. So next time, we'll finish up this proof. It's up there on the board that NL is contained in P and also in log squared n space. There'll be a homework out at some point this afternoon.